let's start from chapter 10. So we have like another 10 slides left from chapter 10. So far we discussed several gas laws. So first one was Boyle's law. And Boyle's law is the relationship between volume and pressure. So this is the only inverse relation. So when it says inverse relation between two variables, volume inversely proportional to the pressure, it's going to be 1 over V. So that's the inverse relation representation in math. This symbol tells us the proportional symbol, and this tells us it's an inverse relation going for opposite direction. Okay, all the other gas laws are direct relation. So second gas law was Charles law. Charles law. Volume is directly proportional to the temperature. So when we increase our volume, temperature increases. So we increase our temperature, increases volume. And also we talk about another law which is called Avogadro's law. Volume is directly related to the number of moles, direct proportional to number of moles. So those are 3 gas laws from what we discussed. So we discussed a few other, but I'm going to use these 3. So now you can see volume is inversely proportional to pressure, volume is directly proportional to temperature, or volume directly proportional to N. So considering these 3 gas laws, we can derive another gas law which is called ideal gas law. Ideal gas law tells us volume proportional to number of moles, it's in the numerator, temperature, it's in the numerator, and inverse relation to pressure. The volume is proportional to those 3 variables, so it's dependent on those 3 variables. So in math, in order to remove this proportional symbol, we can use a constant, and we replace that constant with R, capital R. So in the next gas law, P equal R N D. So this is a constant. Okay. To make it equality, we can put that constant over P. Okay. So by rearranging this equation, we get our ideal gas law. Okay, so P B equal to N number of moles R T. So this R is called universal gas constant. Okay, so this equation is the ideal gas law. So in this equation, we can identify the variation of pressure, volume, number of moles, and temperature. So all 4 variables in the same equation. Okay. It's related to a constant, universal gas constant. So let's go through what are the possible units for R. Okay, so I'm going to rearrange this equation again. P equal nRT. P equal nRT. So I'm going to isolate R on one side of the equation. So divide by NT. Okay. So now universal gas constant is equal to pressure times volume divided by number of moles and temperature. So we discussed the units for pressure. We can use ATM. Volume in liters divided by N, number of moles. Temperature in gas laws always Kelvin. Okay. So if we use our pressure in atmospheric pressure, volume in liters, number of moles, and Kelvin temperature, R value. So this is a constant which is not going to change. And based on those 4 units, this value is going to be 0.08206. It's like this liter ATM per mole per Kelvin. Okay, so that's a possibility for this R value. And also there are other R values depending on the units which we are going to use in this equation. Instead of ATM, we can use our SI units. Okay, so let's go through the SI units. So what is the SI unit for pressure? What is the SI unit? Pascal. Okay. So Pascal abbreviate as PA. Volume. What is the SI unit for volume? Milliliters. Cubic meters. Moles. Same unit. Temperature. Kelvin. Okay. So now we can take our pressure in Pascal, volume in cubic meters, number of moles, and Kelvin temperature. So if we pick those units in our calculation, this R value is going to be 8.314 Pascal cubic meters per mole. Okay, now we can see, depending on our units, R value is going to change because it's a combination of 4 units, actually more than 4 units. Pascal, kilograms, meters per second, so everything in Pascal. Okay, so this cubic meters Pascal, okay, we can derive that unit joules. So Pascal times cubic meters equal to joules. Okay, so we can condense our unit into this again. Joules per mole per Kelvin. So if we go to the next slide, slide 61, you can see different units and different R values. It comes based on the units for other variables. Okay, so these are the possible R values. So depending on your unit in the equation, you have to pick the correct R value. So if I give my pressure in Pascal, unit meters, moles, and Kelvin, that's the R value. So if our pressure in atmospheric pressure and volume in liters, first value is one you need to substitute in the equation. So this law is called ideal gas flow. PV equal to NRT, pressure, volume, moles, temperature, gas constant, or universal gas constant. Universal. You should be able to identify these 5 variables. Okay, let me give you a question from this equation. Okay, so let's calculate the volume of gas. What is the volume of gas? In cubic meters. Yes. 25 Celsius. 2 moles. Solve for volume. The gas is at 25 Celsius, number of moles is 2 moles, and its pressure is 125,000 Pascal. What is the volume of gas in cubic meters? What is the answer? Okay, so we can solve for volume. Volume is equal to nRT divided by C. Number of moles, 2 moles. R, what is the proper R value? What is the R value?
0.8.
Okay, so now we have to look for the units of pressure, Pascal, and number of moles. Okay, so it's dependent on Pascal. So if you go to the table on slide 61, Pascal in fourth column, which is 8.314. The R value which you are going to submit in this equation is going to be 8.314. So this is Pascal, cubic meters per mole per Kelvin. So you're going to pick this R value based on the unit of pressure, because pressure is given in Pascal. If not, you can convert Pascal into ATM and then use the other R value. It's up to you which one is going to use. Okay, you can do that. But again, we need answer in cubic meters. So volume cubic meters. So that's the best R value to use in this calculation. Okay, next one is T. What is the temperature? 25. I got substitute 25 or something else. It should be Kelvin. So it's 25 plus 273. 298 Kelvin is what we need. So that's the value we are going to substitute. Okay, so what else? RT pressure. Pressure is 125,000. So now let's do the calculation. V equal to N, number of moles, 2. Okay, so work with your units, then you can decide whether it's the correct R value or not. So it's moles, R value, we pick this one, 8.314 units, Pascal, cubic meters, per mole per Kelvin, per mole per Kelvin. So times temperature, 298 Kelvin, and divide by pressure. Pressure is 125,000 Pascal. Okay. So now let's see what are the common units. Numerator, same, and the denominator. Moles cancels out. Next one, Pascal in the denominator, Pascal in the numerator, cancels out. Kelvin in the denominator, Kelvin in the numerator, cancels out. Okay. So now answer is in cubic meters. That's the unit we need. What is the answer?
I got 0.039 cubic meters.
Why?
0.39.
This is the answer. That's right. Okay. Yeah. That's the cubic meter volume. That gas has the volume of 0.039 cubic meters. Any questions? Okay, so let me give you another question. If I have 4 moles of a gas at a pressure of 5.6 atm and a volume of 12 liters, what is the temperature? Two. Three. I have 7.7 moles of gas at a pressure of 0.09 atm and at a temperature of 56 Celsius. 56 Celsius. What is the volume of the container? What is the temperature in Celsius? Okay, so let's calculate from Celsius temperature.
What do you have to Celsius to make a Kelvin? It's 290.
73. P equal nRT. Solve for T. Divide by nR. Temperature is equal to P over nR. Temperature. Pressure. Atmospheric pressure 5.6 atm. Volume 12 liters. Divide by n, number of moles. 4 moles. And pick your value. What is your value? So it's going to be the first part. So it's going to be liter atm divided by moles per Kelvin. So it's goes to numerator. Liter atm moles. So final answer is in Kelvin. What is this value?
I got 204.72.
5.6 divided by 4. Kelvin. Okay. Convert Kelvin into Celsius. The Celsius is equal to T Kelvin minus 273. Subtract 273.
Negative 69.
Yeah. Eight point three. Any question? Okay, now we can work on the next question. I have 7.7 moles of a gas at a pressure of 0.09 atm and at a temperature of 56 Celsius. What is the volume of the container that is in that the gas is in? So volume is going to be in liters. and 7.7 R, same R value. Equal 8 ppm. Moles Kelvin times T, temperature 56 plus 33. What is that? Kelvin moles. Volume in liters. What is that?
2,284.
2284. So that what it is it?
Okay, 2,309.
2300?
Yeah, 2,300.
309. Check your math. Any questions? Okay. There will be one or two questions from this equation. Ideal gas flow. Okay, so we did this. Okay, now let's rearrange this equation. So this is the ideal gas flow. PV equal nRT. PV equal nRT. So what is N? Moles. Okay, so how do we find moles from mass? Mass to moles. How do we convert mass of a compound into moles of a compound? True, but what do we need? Molar mass of the compound. So if I give you a question like 25 grams of sodium chloride, convert into moles from grams. So 1 moles of sodium chloride equal to how many grams? So it's going to be the molar mass of sodium chloride. 1 sodium plus 1 chloride. The molar mass, so 58.4 grams. 58. Something. Okay. So by looking at this, we can say moles of a compound is equal to, this is the mass of the compound. Mass of the compound divided by, this is the molar mass. Molar mass. So when we divide mass of a compound by its molar mass, we get number of moles. Okay. This is clear? Okay. So now let's use variables, abbreviations. Moles, simple N. Mass, usually simple M to represent mass. Molar mass, capital M. Okay. And concentration, molarity, again capital M. So sometimes we use the same letter in different equations. So now we can substitute number of moles using these two variables, mass and molar mass, into that equation. So this N is equal to mass divided by molar mass. Let me rewrite this again. PV equal nRT. N is equal to mass divided by molar mass. Now I'm going to substitute this N using those two, mass divided by N. The remaining variable is same equation. And then I'm going to rearrange these equations again. So I'm going to divide by volume, both sides. Cancels out. P equal to mass, and I'm going to write here volume R T N. I'm going to group this. What is mass divided by volume? What is this? Mass divided by volume. Chapter 1 or 2.
So like this.
Density, yes. So that's the density. So now, pressure of a gas is equal to the density of the gas times universal gas constant times its temperature divided molar mass of the compound. Okay, we can calculate the density of a compound by measuring pressure, temperature, and molar mass is depending on the type of the gas. Or we can recognize unknown gas molar mass. So it's a unique number for the molar mass compound. We can calculate molar mass of a gas using density, pressure, and temperature. Same equation. So there are two other forms of this equation to solve for molar mass. Molar mass of a gas is equal to density RT divided by P. So this is the next form of the ideal gas equation. Okay, 4 variables. Yes, 1, 2, 3, 4 variables. And 3 will be given in the question and you're going to solve for 1. The next one is to calculate density of a compound. Pressure times molar mass is equal to RT. So now we can calculate the density of the gas using pressure, molar mass, and its temperature. Again, 3 will be given, and we're going to solve for one of the variables. All those equations will be on the front page. So recognize which equations you need to do your calculation. And pick the R value based on your units. Okay, let me give you a question.
Would this table be in the the
R value?
R value?
Yes, it's in the front page. I already emailed this cheat sheet. Okay, so a 5-liter flask of carbon dioxide gas at a pressure of 4.54 atm had a mass of 35. So the question is how many moles of gas was it consumed? No, not that. Wrong question. Okay, so 500 milliliter flask contain oxygen gas at 25 Celsius at a pressure of 4.5 atm. What is the density? What is the density? Okay, so density equation is density capital Q simple D. So I just write simple D. Density is equal to pressure times volume over RT. Looking at the front page. Oops, sorry, not pressure. Molar mass. Molar mass over RT. Your density unit is going to be grams per ml. Grams per liter. This is going to be the unit, so it's not a common unit. Grams per liter.
What was the grams per liter?
Density, unit of the density, final unit. What is capital M? Molar mass.
The 32.
Yes, it's going to be 32. So oxygen. So it's not going to give you molar mass explicitly. So it might give you the compound name. So oxygen gas, molecular name. So you have to find the molar mass of the compound. So it's going to be 32 times oxygen. And molar mass always has 2 units, which is grams per mole. That's the unit of molar mass. Okay, so next one, pressure 4.5 atm. R, you can pick the R based on other units. T, 25 Celsius plus 273 to 98 Kelvin. Okay, now let's solve for density. Density is equal to molar mass 32. Use your units, grams per mole times pressure 4.5 atmospheric pressure divided by R. What is the R value you are going to pick in this question? 0.0806 units liter ATM per moles Kelvin. Goes to the numerator. So peak temperature. Temperature is 298. Kelvin, moles, ATM. Now you can see unit of density could be grams per liter. What is the answer? So usually density in other places you will see units as grams per ml or kilograms per liter. These are the most common units for density. Okay, then we know the density of what is 1 grams per ml. So this is, we can't compare this with the density of water like 1 grams per ml because it's per liter. Keep that in mind. So it's kind of uncommon unit for density. Okay, let me give you another question. Liter flask of carbon dioxide gas pressure of 4.54 atmospheric pressure had a mass of 36 grams. How many moles of gas are in the flask? So 5 liter. Volume is given. Pressure of 4.5. 36 grams. Mass divided by molar mass. you don't need to use this equation. Sorry, my bad. Simply you can substitute molar mass and calculate moles. You don't need that one. So it's 36 grams carbon dioxide. So you can find the molar mass of carbon dioxide. CO2, 1 carbon, plus 2 oxygen, 44 grams. Okay, so this is the grams of carbon dioxide, 36 grams, divided by molar mass, 44 grams per mole. Okay, so let's calculate temperature. Temperature is not given. So what is the temperature? It's from PV equivalent nothing. What is the temperature? Solve for temperature. So you can find the number of moles from this. It's going to be simple then. In available, volume available, pressure available, or the pressure volume is 5 liters, is 0.81, ah, 88 liters, so it's going to be this direct. At 41.5 Kelvin. Is that enough, or do you need more questions? Okay, so it's just identifying the variables and proper value and substitute those numbers into the equation. Okay, so that's about the ideal gas flow. So this is the other form of the ideal gas flow. We discussed partial pressure from the last lecture, last couple of slides. Several examples, effusion and diffusion. The meaning of these two words. Effusion is the escape of gas molecules through a tiny hole into an evacuated space. So that's the meaning of diffusion. So let's say there's a container divided into two components, make a tiny hole. And this region is empty. And if we fill a gas into this, like hydrogen gas, there are hydrogen gas molecules. So properties of gases, gas particles moving on a rapid straight line. Okay, so rapid motion, straight lines. So when these particles move straightly, they can bump into the wall and bounce back. This, they can go all the way, and at some point, these molecules can go through that tiny hole. So this is the meaning of diffusion. And next thing, let's say there's a gas inside a container, and if we open this container, gas particles diffuse into the open environment. So that's the meaning of diffusion. So it goes through other molecules. Effusion and diffusion. Effusion is escape gas molecules through a tiny hole into an evacuated space. Diffusion is the spread of the substances throughout a space or a second substance. Okay. So why we need those two words? There's another law which is related to the effusion and diffusion, and it's called Graham's law. And we are not going to do any mathematical problems from this law, and I'm not going to give you this in the equation shape. Only thing that you need to understand is speed of diffusion. So it's depend on the mass of the gas particle. So lighter the molecule, it diffuse faster. Okay, so that's the only thing you need to understand from this slide. So let's say there are two gases like nitrogen and oxygen. Which gas diffuse fast? Is it nitrogen or oxygen? Which gas diffuse fast? Nitrogen or oxygen? Nitrogen, because this is lighter than oxygen. 28 grams per mole, then 2 grams per mole. Lighter the gas, diffuse faster. That's it, Graham's law. Okay. Right. Okay, so these are the last law is called ideal gas law. Okay, so it's true for ideal gas. So what are the ideal gas? So ideal gases are the gases which satisfy points in the kinetic molecular theory, which we discussed at the beginning of the lecture. So this is the kinetic molecular theory, which tells us the properties of ideal gas. So there are 5 key points. First one, move rapidly in straight lines. Okay, so it's true for all gases. Have essentially no attractive or repulsive forces. Okay, that's one of the important points. Between particles, no attractive or repulsive forces. But it's not 100% true for real gases like carbon dioxide, nitrogen. So these are real gases: carbon dioxide, nitrogen, any other gas. It's not essentially true. So there are some attractive forces between carbon dioxide and carbon dioxide, or between other gas particles. So these attractive forces are called van der Waals attractive forces. Those are weak, but still there's attractive force between particles. So now these are real gases. These are real gases. And when there's attractive force between real gas molecules, it deviates from the ideal gas flows. So we can't use those ideal gas flows. It's deviate from the ideal gas flow and are very far apart. It's depend on the container. So let's say we have all these particles. So it has like 6 particles in a small container. Okay, this is the size of the container. 6 particles. Now it's not far apart. Okay, it's depend on the container. Have very small volumes compared to the volume of the container. Okay, again, it's depend on the type of the size of the container. Have kinetic energies that increases with an increasing the temperature. So this is true for real gas. This is true, but this is not entirely true. It's not again entirely true. Again, not entirely true. So some of these real gases they will be deviate from ideally. Okay, so how do we make these real gases into ideal behavior? Okay, so then we can use those ideal gas flows. So let's say we have a gas in a container like this. Okay, let's say it's 3 particles, and the same gas or same amount of gas in a container like this. So it's the same gas in 2 different containers. So now these particles are close to each other in this container, but it is not close in this setup. Okay, what did I change? Its volume. So how does volume affect? Volume is inversely proportional to the pressure, Boyle's law. When I increase my volume, pressure decreases. So volume increases, pressure decreases. So now you can see if this is like hydrogen, real condition. When it is at low pressure, it's close to ideal behavior. So this is low pressure. Okay. The next one is particle motion. So when two particles are close to each other like this, okay, then that's a chance to have those attractive forces. So if I limit the time, these two particles going to stay close to each other. If I limit that time, I can reduce the attractive forces. Then it has to move faster. So how I can speed up this particle? How do I speed the speed of the particle? Temperature. That's good. Okay. So anything in motion has a form of energy. It is kinetic energy. In order to increase kinetic energy, I need high temperature. So again, at high temperature, real gases behave like ideal gas. Okay, so if there's a real gas with low pressure and high temperature, I can use this gas also. So it's close to ideality. That's what you see in the next slide. In the real world, the behavior of a gases conforms to the ideal gas equation only at relatively high temperature and low pressure. So that's where we can apply this gas law. Because the real gas is at relatively high temperature and low pressure, these equations are valid. If it is not true, it's deviate from the ideal. Okay, so this is the ideal gas law, ideal condition. So if it is different pressures and different temperature, there are different deviation. It's depend on the type of the gas. So again, there's another equation derived for real gases at any temperature and pressure. Okay, so there are some correction factors for pressure and volume, which we are not going to talk about. If you are going to learn Chem 2, you will learn that equation. So we can add some correction terms for pressure and volume. That's the real gas or non-ideal gas equation. It's called Van der Waals equation. Okay, so the same thing explained in the next slide or last slide. At low pressure and high temperature, gas behave as ideal, and in this condition, it does not behave as ideal gas. Any question?